Okay, so we start with 5.3, big day, fundamental theorem of calculus. Oh, wow, fundamental theorems. There's no fundamental theorem of geometry, I'm aware. We kind of start with these axioms, like, for example, shortest distance between 2 points is a line, yeah. So there you go. So a lot of geometry is based off that principle. How many points does it take to create a plane? 3. Need at least 3 points, and the 3 need to be non-collinear, so they can't be on the same line. So there's things like that for geometry. They're kind of fundamental to its development. A for the day, who remembers the fundamental theorem of algebra? Your beloved algebra. Uh-oh. No. Good try. Hi. Thank you. No, it's not. What? You have something important to do. Don't write this down. That ring a bell? How many solutions does that? 5. That's the fundamental theorem of algebra. When you see the degree of a polynomial, that's the number of solutions that it has. That's the fundamental theorem of algebra. We've done that many times, right? You just don't remember it. So anyway, fundamental theorem of calculus is a little bit different. It comes in 2 parts. We're actually going to do part 2 today and part 1 tomorrow. I know that seems backwards, but that's the way I roll. So here we go. We're going to call this the function y equals f of x. I don't like the f of t. And actually, I'm going to back that up just a little bit. Call that x. I'm going to call this x plus h. And we've been talking about area, right? So we're going to call this shape here an area function. Whoa. That means as I move this x plus h further to the right, what's going to happen to the value of that area? Increase. As I move it closer to x, it will decrease. Okay? So you can kind of see what's happening here. So it's a function, meaning it changes given different values. So I have area in terms of x is equal to the integral. If I want to figure out this area, what I could do is I could figure out this red portion by bringing it all the way back to 0. And then what would I do? Subtract off the stuff up to x, right? And I would subtract that. Okay, so the integral because if we don't do it like that, then we can't get kind of the proof argument that we want. Okay, so we're going to say the integral from 0 to x plus h of the function f of x dx minus the integral from 0 to x of f of x dx is equal to that area piece left over. Everybody okay with that? Okay, now I'm going to do something that might make you a little bit uncomfortable, but I got to do it. And that is, what is this distance right there? H. Very good. And so, before we've talked about kind of estimations using right hand, left hand, midpoint, all that piece. Suppose I looked at a left hand sum here, and I looked at the height times the width. What's the height of that rectangle? F of x. So would you agree that the area function is approximately equal to the width times that height. And as I move h closer to 0, those two are going to become the same eventually, right? So therefore, I can replace this a of x with h times f of x is equal to the integral from 0 to x plus h of f of x dx minus the integral from 0 to x of f of x dx. Well, wouldn't it be neat if we could say something interesting about the function? Like, if given the function, it then said something important afterwards, that would be valuable. So I'm going to divide both sides by h. And I get f of x is equal to the limit as h goes to 0, because we want to draw h closer together, of the integral from 0 to x plus h of f of x dx minus the integral from 0 to x of f of x dx all over h. And that's when I asked you, does that look familiar? What, Kyle? That deserves a round of applause. I mean, that, yep. Mercedes is impressed. She's going to ask you for an autograph later. I would start charging. So you're absolutely right. This is the original derivative, right? Remember the limit as h goes to 0 of f of x plus h minus f of x all over h, right? You remember that? If I write it on board, you have to remember. Okay, so I'll try again. Mercedes, don't shut down on me. Tell me you remember that. All right, yeah. So what that means is what we plug into the function, when we do this, we get the derivative, right? So we'll see what you know. When you take the derivative of that, or when you do this, does anybody know what you come up with? What's the function? The function is x squared, right? The function is x squared. When you take the derivative of x squared, you're going to get 2x. This ends up being 2x. What about the limit as h goes to 0 of sine of x plus h minus sine of x all over h? What are you going to get there? Cosine of x. Now, that's some difficult argument pieces there. We actually had to use the sandwich rule in order to figure that out. It took a whole day, basically, to figure that out. But whatever this is, see, function, when you do this, you get the derivative. Function x squared, when you do this, you get the derivative. Function, when you do this, you get the derivative. Now, if you don't believe me, multiply this out. X squared plus 2xh plus h squared minus x squared all over h, you're going to get 2x. If you don't believe me, work it out. We did many problems like this, didn't we? So, this is the function. That's the derivative. You got that in your brain? Now I'm going to flip back. Look, folks, that's the function. That's the derivative. This represents area, right? The area bounded from 0 to x. When you take the derivative of the area function, you get the function that sits on top. Statement about f of x. The derivative, or f of x is the derivative of the area function. So what that means is if you have an area function 0 to x of f of x dx, and you want to take the derivative of it, you would get the function. So what does that mean? Well, often in these problems, we're given the function, right? So that means in order to come up with the area, we have to come up with the thing that you took the derivative of to get it. For example, if I give you 2x, what did you take the derivative of to get 2x? X squared. So if you're given the function, you got to find what you took the derivative of to get it. The area function is an antiderivative of f of x. Again, the chief piece that you'll have to focus on if you truly want to understand what the heck it is that we're doing and why we're able to get there, this is what you have to kind of think about for quite some time. But let me give you the classic example that we started out with. The area bounded from 0 to 2 of x squared dx. And we came up with 8/3. Well, isn't that interesting? Think for a second, folks. What do you take the derivative of to get x squared? It's going to be an x to the, it's going to be x to the third something, right? Anybody think of the constant that's missing here? What would you have? What would you take the derivative of to get x squared? What? Yeah. Well, plug in 2. What do you get? 8/3. Oh boy. All right, so if I have a function and I call it x to the n, okay? We'll do a couple examples here. No, just watch, just watch. We'll get to the note right. Just to truly try to think of what's happening on the board, okay? So if my function was x squared, okay, and you took the derivative, you got 2x, right? So if my function is x to the nth, the derivative, does anybody remember the formula? N times x to the n plus, or yeah, n minus 1. So look at what Allison just said. She said it's 1/3 x to the third, or x to the third over 3. So we'll call that big f of x. It's the thing you took the derivative of to get little f. So what did you do to the exponent? You added 1, and then you divided by the exponent. Doesn't really work out if you do that. So this is the idea. You guys, we've spent all first semester moving forward. We've been doing differential calculus. We've been moving from here to here. Now, second semester, we're going to be moving from here backward. And that's super exciting. The problem is you give me a function, I can find the derivative, I promise. But if you give me a function, there's a whole bunch of them I don't even know the antiderivative of. But we're going to give you easy ones. So let's start with that. Let's try a couple problems, okay? So, flip it over. Okay, I forgot to write the bottom part. All you want to write there, the fundamental theorem of calculus, this is going to be tomorrow. And part one is just a better explanation of what I wrote up there. So all you need to write down here is the antiderivative of x to the n is exactly what we said, which is f, big F, is equal to x to the n plus 1 over n plus 1. That's the antiderivative formula, the general rule for a power function. Okay, that doesn't tell us about sine, cosine, tangent, or natural log, or e to the x, or anything like that, or 2 to the x. But it does tell us about general power function rules. Okay, so let's put this into play. Find an antiderivative for the following. Well, if f of x is equal to x to the third, you know that f prime of x is 3x squared. But we don't want to know f prime of x. We want to know big F of x. Moving up in the world. So if x to the third is my function, what's the antiderivative? Raise the exponent by 1, and you get, and then divide by the new power. That's the antiderivative. If you don't believe me, take the derivative, and you should get that. Now, it's an antiderivative. There are an infinite number of antiderivatives that would give you that for a derivative. For example, f of x could also be x to the fourth over 4 plus 10. Would you agree that if you took the derivative of either one of these, you would get x to the third? Why? So the derivative of a constant is 0, okay? So that's the big idea. So we're just going to write the most general one. Antiderivative of 5x to the fourth. What do you think? Yeah, 5x to the 5 over 5, so just x to the fifth, right? Going backwards, huh? Yeah. So we're going to increase the exponent by 1, and then we divide by the new exponent. Yeah, they just come along for the ride. They're just excited to be part of calculus, wouldn't you be? You are part of calculus, Hannah. Okay, this one, f of x. Antiderivative 4x to the 6th. 4x to the 7th over 7. No simplification, so that's what I got. For the next one, I don't like that the x is in the denominator, so I'm going to write it as 3 over 2x to the negative 3. And so I should increase the exponent by 1. When you increase it by 1, you get x to the negative 2 divided by negative 2 over 1. Now I should multiply by the reciprocal, and I get big F is equal to negative 3 over 4, and I'll drop the negative to the denominator, so negative 3 over 4 squared. Got the idea for general antiderivatives? Come on back, and then we'll learn fundamental theorem of calculus part 2, and bring your seatbelt because it will be amazing. Yeah. I can show you quick. Okay, so we pick up with the fundamental theorem of calculus part 2. It says this: the integral from a to b of f of x dx is equal to. So before we used to write that thing, right? The infinite limit, Riemann sum. That's what we used to write. We don't have to write that anymore. That took up a half a page of paper when we would do it, right? When you talk about work, that was a lot of work. So what it is f of b minus f of a, where f is any antiderivative of little f. So all we need to do is come up with an antiderivative. Okay? And once we do, we just evaluate both bounds. That's it. Piece of cake, upside down. So let's put our plan in action. The problem that we looked at before. What's the antiderivative of x squared? X to the 3 divided by 3. Then we write a bar, vertical bar. And at the top, put the top bound, and the lower part, put the lower bound. That means that we evaluate the function at these spots. That's what that notation means. We plug in 2, we get 8 over 3. Plug in 0, we get 0 over 3. We subtract the results. And that's all there is to it. That's the exact area bounded beneath the curve x squared between the x values 0 and 2. Yeah. We're doing the exact same stuff that we did last week. It's just now we're using another application of calculus, namely the fundamental theorem of calculus, instead of the infinite limit of Riemann sums. What's the antiderivative of 3x squared? X to the third. We evaluate it over 3. Evaluate it. What is 4 to the third? 64 minus 8, which is 56. Colton, you had a question? Okay. All right, the next one. I'm going to rewrite this as the integral from 1 to 2 of 3x to the 1 half dx. What's the antiderivative of 3x to the 1 half? Right, is 3 over 1 x to the 3 halves divided by 3 halves. Well, because I'm going to multiply by the reciprocal. I mean, this is over 1, is it not? So I'm going to just use it to help with my arithmetic. Multiply by 2/3. And so the 3's cancel, leaving you with 2x to the 3 halves evaluated at 1 and 2. So 2 to the third, 8 square root, 2 roots of 2 times 2, 4 roots of 2. Minus, we'll get 1, 1 to the third, 1 square root, 1 times 2, 2, 4 roots of 2 minus 2, that's the exact value. Look at the next one, there's 4 terms. Imagine, had I given you on your assignment one that involved 4 terms. That would have taken us a little while, right? And I could have, even, instead of starting 0 to 1, I could have gone, say, 1 to 5. That would take a long time. But using the fundamental theorem of calculus part 2, it's really quite easy. What's the antiderivative of x to the third? 4 over 4. Minus x to the 3 over 3 plus x squared minus 3x. Does everybody see that the antiderivative of 3 is 3x? So it'll be 2x to the 2 over 2. Okay, so 3 is 3x to the 0. So if you increase it by 1, you get 3x to the 1 and divide by 1. So you get 3x. So the antiderivative of 3 is 3x. Most people just recognize that, what do you take the derivative of in order to get 3? That'll be 3x. Evaluate at 1 and 0. I get 1, I get a fourth, minus a third, plus 1, minus 3, or I guess common denominator would be 12, so 3 over 12 minus 4 over 12 minus 24 over 12. 1 minus 3 is negative 2, so that'll be negative 24 over 12. So 3 minus 4 is negative 1, minus 24 is negative 25. Negative 25 over 12, or negative 2.083 repeating is what we're going to check that decimal as. Take out your calculator, and let's look at it. What's different about this answer? It's what? It's negative. We're going to plug in our function, x to the third minus x squared plus 2x minus 3. And if I do that, I'm going to zoom standard and look at the function from 0 to 1. Is the function below the x-axis or above? So therefore, the area will turn out to be negative. Second, calculate, and we're going to do number 7. We're going to go from 0 to 3. Oh, 0 to 1, right? Let's try it again. 0, 1. And then we get negative 25 twelfths. Area can be negative when we talk about different things in the world that relate to negative numbers. Oh, this is where I went on my rant. Quite cool. So, 2 more examples, and then you get your worksheet. Worksheet, because I know you like to work on your math in other classes. So, yeah. All right. The integral from 0 to pi of sine of x. I'm going to graph this really quick. We've actually looked at this one slightly before. What's the period of sine? 2 pi. Thank you. And so we're going to divide up into 4 parts. And as you divide up into 4 parts, we know its top value is 1, its bottom value is negative 1. And we know that the graph looks like that. So we're wondering that area right there. Hi there. And that's the big question. So, well, we don't have any formulas over here. We couldn't do the Riemann sum piece, could we? Even if we tried. No. In fact, we used our calculator for approximation pieces. And so, well, let's not approximate. Let's do it exactly. What's the antiderivative of sine? Negative cosine. Because the derivative of a cosine is negative sine. So you have to use a negative cosine of x. We're going to evaluate that at 0 and pi. Because you guys are so smart, you remember the exact value of cosine in all sorts of spots. For example, this coordinate right here is 1, 0. This coordinate right here is negative 1, 0. And is cosine the y value or the x value? It's the x value. So what's the cosine of pi? Negative 1. Yes. What's the derivative of negative cosine? Positive sign. Positive sign. Yep. Yes. Derivative of cosine is negative sine. So the derivative of negative cosine is positive sine. It's not a polynomial, so we don't want to apply the power rule. You get that cough checked out. Okay, what's the cosine of pi? Negative 1 times negative would be positive 1. Minus, what's the cosine of 0? No. 1. It's the x value. And then a negative, so minus a negative 1 is 2. The area is positive. You can see right there, you know it's not going to be 0. What if I would have asked for the area instead of going 0 to pi? What if I went from 0 to 2 pi? What do you think the area would have been? It would have been 0. because the positive and the negative are symmetrical. They are the same, and so they would have canceled each other out. No, it's kind of like this. Watch. Okay, so you ask a really good question. No, 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 don't give me the whatever. Okay, here, this works out. Okay, area can also refer to distance that you've traveled. Okay, now watch. What? This is the example. I'm going to walk a distance forward and backward. What is my displacement? 0. Well, what is the total distance I traveled? It would be the absolute value of those two pieces, right? And so that's what we'll do later on. So it comes back to that displacement at, opposing distance piece. You know what I mean? So positive accumulation of snow and then melting snow. You know what I mean? So anyway, okay. All right, last one. F. All right, what's the antiderivative? I got 2x to the negative 2. What to do? It'd be 2x to the negative 1 divided by negative 1, or 2 over x, right? Sometimes you just got to make a space to do some scratch work for your antiderivative. So you got 2 over x evaluated at 1 and 5. Look at 5, we got 2/5. Minus. Oh, yeah. Thank you. Sorry, negative 2 over x. So it's negative 2/5 and then plus 2, or negative 2 over 5 plus 10 over 5, which is 8 over 5, or 1.6. Now, on your assignment, I'm also going to ask you to sketch a graph. You can look at your calculator if you want to be able to see what the region looks like. And the graph of 2 over x squared, hopefully you remember from your great college algebra course that you had last year, that that's a graph of 2 over x squared. X squared is going to bring them both to the top, and from 1 to 5, so it's something like that. So how will you know if your answers are right? You will check these on your calculator. I will make an answer sheet as well, where you'll plug in 2 divided by that x squared piece. And you, type in calculate number 7, and it shows you the graph. If you don't like the graph, maybe you want to change your window so that maybe your y values only go, say, negative 2 and positive 2. So I'm going to second calculate, and I choose number 7. And the lower limit is 1. The upper limit is 5. I get the exact value, which is 1.6. I mean, come on, that's impressive, you guys, isn't it? I mean, we don't have to do that infinite limit of Riemann sums anymore. Now, some people speak ludicrous at this point, and they're like, oh, Mr. Gens, I like the Riemann sums better. They were easier. You can like them more, and that's fine. I actually enjoy doing those more. I like the calculus behind it, but it ain't easier. There's no time in my life have I ever said, oh, well, I guess I'm going to do that one instead of the, calculus fundamental theorem part 2. I don't do that. So, okay, do the one you should do. Last part. Question of the day. dx. Do you see it? What happens to that dx? It just goes away, doesn't it? Because here we got negative cosine of x evaluated at pi and 0. So here's my attempt to quick show you why we attach a dx. What this means is that this is a derivative of something. What do you take the derivative of to get sine of x? Negative cosine. The dx means this is a derivative of something. Like if I gave you y squared is equal to x, what's the derivative of y squared? 2y prime is equal to 1. So instead of a y prime, you could attach a dy instead. It's the same thing. That means that this 2y dy is a derivative of y squared. So that's what that notation means. Notice when we go reverse, we don't attach the dy with it, okay? It means it's a derivative of something. Okay, worksheet for your assignment. I hand it to you right now.